So we're going to keep building up in families. We have a lot to go through. We've done 3. We're going to do cycloalkanes, cycloalkenes. After this, the next lesson, we'll get into aromatics, which are a 6-membered ring. Then we'll get into the whole alcohol family. Maybe have a little alcohol discussion. Organic halides, carboxylic acids, and esters. Okay. They're all families. Okay. So 2 separate families in this heading. These are hydrocarbons can form ring structures. Okay. To name them, in front of the stem, we add cyclo to tell the reader to put it in a ring and not in a straight line. We need a little bit more rules if there's a double bond, because we don't have an end to count from. So IUPAC, who makes the rules that we all follow, says if you have a ring that has no end and there's a double bond, the double bond is going to be in the 1 position. And then we're going to build off that. Okay. Now, we would always want to minimize the numbers from an end. Okay. Here, we'll minimize the numbers going around the circle. So let's look at kind of these rules in action. So we have a cycloane on the left. There's all single bonds in that ring structure. Okay. Now in rings, you don't try to find the longest chain. The ring must be the stem or the parent. Okay. Do not zig in and out of the ring. Okay. There are no branches here. The only thing we have to deal with is that ring structure. So we'd name it like we would before, but add cyclo. So we have 1, 2, 3, 4, 5. So that is pent. All single bonds. So pentane, but it's not in a zigzaggy line. It's in a circle. So we put cyclo in front. And that'd be it for that cycloalkane. So I started a bit simple with the ane example on the left. We've got an ene on the right to deal with, but it's way more complicated. We've got a double bond, and then we've got 2 alkyl or Si groups to deal with and number properly. Okay. Now our sequence hasn't changed. Find the stem or the parent, deal with the ending, and then deal with branches. So we don't zig and zag in and out of the ring. The ring is our parent. There's 1, 2, 3, 4, 5 again. So this is another cyclopent. But it's not an ane, it's an ene. Okay. Now I'm not going to write a number because IUPAC says that has to be the first carbon-carbon bond in our counting. We didn't have this type of rule in our linear structured molecules. So I'm going to have to deal with the branches now. Now I like to box up my branches. That's just a personal strategy. I'll continue to do that. Boxing them up helps reinforce that there's 2 separate branches coming off 2 separate pieces of our parent. They are both methyls, so we can name them together. If they were different, we'd list them alphabetic. Two of them, so di, tri, tetra, di is the 2 of them prefix. And we're going to need 2 numbers. So there's 2 ways to go around a circle. I or you would have to think of both ways and minimize the count. I'm about to draw both of them. I would only put the proper one in your notes. So I may erase what I first write. I'm going to go across the double bond counterclockwise first and see what I get, and then I'll compare it to the clockwise version. Let's see. So if I go across my one bond, this would be the first carbon, the second, the third. First, second, third. The first methyl would be in the 4 position, and the second one would be in the 5. That's what I get when I cross the double bond and go around to my methyls. This would be my 1 carbon, my 2, my 3, my 4, and my 5. Okay. So that's one option we have to keep in our brains, but we have to compare that to the other way. What if we go this way? I'm crossing the double bond again, but I'm going clockwise now. Okay. This would be the first carbon, the second, the third, the fourth. So what was it? 4, 5 the other way. This way is 3, 4. Clockwise has lower numbers, and this is the way IUPAC says we have to number it. So we have to go the direction that minimizes the numbers. So 3, 4 is lower than 4, 5. There's no rule that says go clockwise or counterclockwise. The rule is minimize the numbers. So we have our correct name when we considered the two ways. Okay. One error you might make is not going across the double bond. Your first and your second carbon have to be on each side of the double bond. So make sure you don't start next to the double bond and then go. If I start at that purple dot and head clockwise, I've never crossed the double bond. So that would be incorrect because I haven't crossed it. Cross it and then keep going. Okay. So we've quickly gone through 2 more families. Now I'm going a bit quickly through the families, but we're going to keep having these rules being emphasized over and over again. So again, after about 2 or 3 more lessons, you're going to get really used to looking at the stem, looking at the ending, putting in alkyl groups. So that's why I'm going a little bit quick. Okay. And now that we've gone through 5 groups, I always do a summary of some of the patterns we see. Okay. There's some generic patterns or formulas that I want you to be aware of with these 5 hydrocarbon groups. Okay. So you're going to want a table with 5 rows. We'll talk about that generic pattern. I'll do an example. And then on the far right, I'll talk about whether they're saturated or not. So the whole alkane family follows a CN, where N is the carbon count. The hydrogen count will always be double plus 2. So an example of how we can quickly predict the carbon count, if I have propane, C3, I don't have to draw this out to know how many hydrogen if I know it's propane, A-N-E. I can take the carbon count, which I'm calling N, and double it and add 2. So 3 times 2 is 6 plus 2. The molecular formula would have to be C3H8. We can predict that really fast. Okay. Now, anes have all single bonds. You have the most amount of hydrogen possible, so these are saturated with hydrogen. Okay. And we just use the term saturated. Okay. Saturated fats don't have doubles or triple bonds. They also turn into solids more easily in our bloodstream, which is bad for our blood vessels and heart. Okay? Unsaturated fats are more likely to be liquid. That's alkanes. We're going to move to the alkene family. We've added in a double bond. Okay? We've taken away two H's to put in that double bond. We have a 2N hydrogen count compared to the N carbon count. So we get a different type of molecular formula. If we have 3 carbons, so we've propene, ENE, the hydrogen count will have to be 6. And this is unsaturated. It is unfilled with hydrogen. Okay. The double bond has removed some hydrogen. We'll kind of continue this pattern with alkynes. We went from a double to a triple bond, and we had to take away 2 more hydrogen to have room for the third bond. So we get a 2N minus 2. No, the enes and the ynes are only applicable to 1 double or 1 triple. This doesn't work. If there were 4 triples, this wouldn't work. If we have propyne, YNE, the hydrogen count is going to be 2N, which is 6, minus 2. There's only going to be 4 H's. You should be able to identify the family based on the hydrogen count. Okay. Now these propynes are also unsaturated. So maybe I want to test your knowledge of this. I give you a C50H100. Okay. You can tell what family that is. You certainly wouldn't want to draw it. Okay. C50, that's going to take you a while. Put in 100 H's. Maybe takes you 15 minutes to draw it. Total waste of your time. You'd want to think of the pattern. Think of this CN. The H would be, what, 50 to 100. That's a double. So that's a 2N. So that fits the ene pattern. Okay. That is an ene. That is unsaturated. No need to draw it. Okay. Well, that was our first 3. I said there's 5 families we've done so far. So I'm going to keep going to the cycloanes. And we get a repeat in the generic pattern, or an overlap. Single bonds, but in a circle, are also CnH2n. So the smallest cyclo I can have would have 3 carbons. You can't make a ring out of 2. So cyclopropane would be C3H6. If you have 3 carbons in a row with 3 H's at the end, when they make the ring and the carbons connect, you have to lose an H at each end to go from a straight chain into a ring. And that's why you don't have the +2 in cycloanes. It's the making the ring pops out some H's. Okay. Now these are still deemed to be saturated. For the ring, it's got the most hydrogen it can have. There's no double or triple bond, so the saturated term is still used. Last, we have the rings, but there's a double bond. We lose 2 H's to put in the double. And we've completed our generic formulas for our first 5. Now we're going to use this concept to answer isomer questions. We're going to do drawings based off molecular formulas, and we have to realize what pattern might we have. Okay? What if you're given C50H100, like I gave you before, what would we consider? If we're trying to name or draw C50H100, CnH2n, we should be only considering alkenes, or we could have cycloalkanes. There's no way you're going to have one triple bond in a C50H100. It's just impossible. There's too much hydrogen to fit in the triple. So those two kind of pair up. You also get overlap with the 2n-2s. Something with a triple bond has the same pattern as a ring double bond. And then we've got the alkane family with the 2n+2 that overlaps with nothing. If you have a 2n+2 pattern, you know you have an alkane. There's no other possibilities for what it could be. Again, this is handy. I'm about to do an isomer question. Okay. Isomers are different structures, so drawings, okay, of substances with the same molecular formula, which is like C3H4, okay, or C50H100. Okay. There's lots of ways you can draw a C50H100. Okay. All those different drawings of C50H100 are isomers of each other. And we're going to apply our generic formula knowledge. We're going to learn about isomers as I draw every single isomer possible of C4H8. And this is a very common diploma question. Draw all the isomers of blank. I just don't know what the blank will be on the diploma. Okay, so isomers, this is what I'm doing, different structures. I'm going to hide that. I need to make a good plan, because if you sit there and you try to draw anes and enes and ines and cycloanes and cycloenes, you'll never finish the exam. That approach will not work. We need to think of this pattern. C4H8, 4 to 8 is a double. This is the CnH2n pattern. So the isomers are going to fit into one or two categories. Let's see, what's the 2n plus, or the 2nH2n? That's the 2 green stars. I should only try to draw enes and cycloanes. And I'll do all of one type, and then I'll do all of the second. So I'm going to make a little note of myself, so a note for myself. Enes are one of the categories, and cycloanes are the other that follow this pattern. And I'm going to start with how many different enes can I draw that have 4 carbons and 8 hydrogen? Okay. I'm going to start with all 4 in a row, and then I'll try 3 in a row and then 2 in a row until I can't make it work. So let's see, how many different ways can I put 4 carbons in a row? That's the C4, and then it has to be an ene, so I need to put in a double bond. Okay. So that's a C4H8 double bond. I'm not going to draw my hydrogens in, but I'm going to put dashes where all the hydrogens would be. 1, 2, 3, 4, 5, 6, 7, 8. Okay, better work out because enes have to be, for 4 carbons, there has to be 8. Okay. So that's one of the isomers, one of the C4H8s. Let's see, this is bute 1-ene is the name of one of the isomers. Okay. But that is not the only structure or name of a 4-carbon double bond molecule. I could move that double bond around. Okay. I could stick to the 4 in a row, but I get a different isomer if I move the double bond to the middle or over 1, which is the middle. 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. C4H8. And now this is a different structure because it has a different name. It's a butene. And there's no other but blank enes that I can draw. There's the 1 and the 2. If I move the double bond all the way over to the far side, that would be 1 from the end, which would be a but 1-ene again. Okay. So there's only 2 isomers so far. I'm going to take away that black arrow. I could do but 1-ene, I could do but 2-ene. Okay. So I've done all the isomers that have 4 carbons in a row. So I'm going to drop the carbon count down and see if I can still make it work. Can I put 3 carbons in a row and use the 4th as a branch? Okay. C4H8, they don't have to be in a straight line. It just has to have 4. So there's 3 of them. I need to have a double bond. And can I put a branch into this? I can't put branches at the ends because that would be part of the longest chain, but I have a nice spot in the middle I could put my last carbon. 1, 2, 3, 4, 5, no room in the middle, 6, 7, 8. Yeah, good, it worked. It had to work, okay, because this is a C4H8 with a double bond. Now, what on earth is this? 3 carbons in a row. So that's a prop. There's a double bond in the 1 position. Okay. But in propene, the double bond has to be in the 1 position. There is no 2 position allowed. Okay. If I wrote the double bond on the other side, it would still be the 1 position. It'd be 1 from the right instead of 1 from the left. So I'm not putting a number in because prop-2-ene doesn't exist. Okay. I need to describe that branch. Okay. That's a methyl, a 1-carbon branch. And that branch is not allowed to be at the beginning or the end. The only possible spot that branch can be is in the 2 position. And because 2 is the only possible methyl, I'm not going to write that 2 either. So the double bond has to be in the 1 position. The methyl has to be in the 2. I don't need any numbers. And I think I might be out of double bonded C4H8s. I can't put that methyl anywhere else. Okay? Please don't draw this. If I go down to 2 carbons with a double bond, and I try to put in 2 more carbons as branches, I'm going to fail. I can't do it. Okay? I can't put in, if I try to put 2 more carbons in as branches, well, that's just one continuous chain. So I am done with my isomers of double bonds. 3 is the count of isomers so far. I came up with 3 different enes. I'm not done the problem, but I'm well through it. I've done all the ene options. I just have to look at how many cycloanes I can do, and then I'm done. So let's tackle that. We could put 4 in a ring and then try to go 3 in a ring and try to put 2 in a ring and then go, well, that's stupid. You can't put 2 in a ring, and we'll have to stop. So we got to look at 4, look at 3, and then we'll have to stop. So 4 in a ring, and we better have 8 H's. 1, 2, 3, 4, 5, 6, 7, 8. Good, that works. So that's our 4th isomer in total. Cyclobutane. Okay, notice there's no more enes anymore. We left that family. And there's no other 4-membered rings I could do, so I'm going to try a 3-membered ring. 1, 2, 3. Cyclopropane. I have a 4th carbon, and I can stick in a 4th carbon. 1, 2, 3, 4, 5, 6, 7, 8. Good. C4H8. Let's see if I can fit this in. Methyl, cyclopropane. Just made it. No, I didn't put a number in front of the methyl. On rings, there's no beginning or end. When you have one side group, that side group is always denoted in the 1 position. That hasn't been mentioned yet. But side groups will be in the one position. So whether I put that methyl on the top, the right, or the left, it's going to be in the 1 position. Okay? So it doesn't matter where it goes, they're all the same. If I lock that together, we can kind of see that by rotating it. So that's methyl cyclopropane with the branch on the top, but I can move the branch to the bottom right, and it's still the same structure. I haven't changed the bonds, or I can move that to the bottom left. It doesn't matter where I put it. It's the only structure. They're the same. Okay? Or you could flip it right to left, and it's still methyl cyclopropane. So there's no other places I can put that methyl group, so that's it for the cyclopropanes, and cycloethane doesn't exist. 2 things don't make a ring. So it's been long, but we are now done. Now your diploma is sadly multiple choice. So if this was on a diploma, that'd say how many isomers are there of C4H8, and they'd go 4, 5, 6, 7. And sadly, if you miss one, you're wrong and you get 0, which I don't necessarily like, but that's the downsides of multiple choice. If I give this on a quiz and you miss one, well, I could give you, 1.5 out of 2. Okay? But ultimately for diplomas, you've got to be able to get them all and not miss any. So that's why you need a nice systematic approach. Deal all with one family, deal all with the others. If you get a 2n+2, then you're only dealing with the anes, one type. Okay? So that's generic formulas, which are handy, and they're incredibly important for doing our isomer questions.